Welcome to the world of calculus. In this video, we'll embark on a journey through the foundational ideas that shape first semester calculus. Whether you're new to the subject or looking to strengthen your understanding, we'll break down the essentials, starting with numbers and functions and moving through limits, derivatives, and beyond. Calculus is not just about solving equations, it's about understanding how things change and interact. Let's begin by exploring what numbers really are and why they matter in mathematics. Numbers are the building blocks of mathematics. We start with positive integers like 1, 2, 3, and so on, then include 0 and negative integers. Together, these form the set of integers. But mathematics doesn't stop there. By dividing integers, we get fractions or rational numbers like 1, 2, or minus 3, 4. These can be added, subtracted, multiplied, and divided except by 0, and the result is always another rational number. However, not all numbers are rational. For example, the square root of 2 cannot be written as a simple fraction. This leads us to the concept of real numbers, which include both rational and irrational numbers. Real numbers can be represented as infinite decimal expansions. Some fractions like 1/3 have repeating decimals, while others like 1/7 repeat in longer cycles. Irrational numbers such as the square root of 2 have non-repeating, non-terminating decimals. Calculators can only show a finite number of digits, but mathematically these numbers go on forever. The idea of infinite decimals helps us understand the continuum of real numbers, which is crucial for calculus. To make sense of real numbers, we often visualize them as points on a straight line, the number line. The origin is at 0 with positive numbers to the right and negative numbers to the left. Every real number corresponds to a unique point on this line. This visualization helps us understand intervals, distances, and the concept of continuity, all of which are fundamental in calculus. In calculus, we often talk about sets of numbers, especially intervals. An interval is a collection of real numbers between two endpoints. For example, a b means all numbers greater than a and less than b. If we include the endpoints, we use square brackets, a, b. Set notation allows us to describe these collections precisely, which is important when defining domains and ranges of function. Sets can be combined in different ways. The union of two sets includes all elements from both, while the intersection includes only those elements common to both. For example, the union of 1, 3 and 2, 4 is 1, 4, while their intersection is 2, 3. Understanding how sets interact is key when working with domains, ranges, and solutions to equations in calculus. Function is a rule that assigns to each input exactly one output. To define a function, you need a rule and a domain, the set of inputs for which the rule makes sense. The outputs form the range. Functions can be described by formulas, tables, graphs, or even words. For example, f(x) equals square root x is defined for all non-negative real numbers. Understanding functions is at the heart of calculus. Functions are defined by different rules on different intervals. These are called piecewise functions. For example, gx might be 2x for x and x2 for x greater or equal to 0. Linear functions like f(x) equals mx plus n have graphs that are straight lines. The slope m tells us how steep the line is, and n is the y-intercept. These basic types of functions set the stage for more complex behaviors in calculus. Given a formula, the domain is all values where the formula makes sense. For example, hx equals square root x is only defined for x greater or equal to 0. The range is all possible outputs. For fx equals 1x2, the domain is all real numbers except 0, and the range is all positive real numbers. Being able to determine domain and range is a crucial skill in calculus. Functions aren't just abstract ideas, they describe real-world phenomena. For instance, the position of a moving object over time can be described by a function xt. A biologist might use mt to represent the mass of a cell as it grows. In each case, the function's domain is the set of times for which we have data, and the rule is how we measure or calculate the output. Graph represents a function if and only if no vertical line crosses the graph more than once. This is called the vertical line test. It ensures that each input has only one output. For example, the graph of y equals x3, x passes the test, but a circle does not since a vertical line may intersect it twice. Not all functions are given by explicit formulas. Sometimes a function is defined implicitly by an equation like x2 plus 2y3 equals 0. Solving for y gives us the explicit form. Inverse functions reverse the process. If f(x) equals y, then fy equals x. For example, if f(x) equals 2x plus 3, then f(x) equals x3/2. Understanding implicit and inverse functions is important for solving equations and analyzing graphs. Trigonometric functions like sine, cosine, and tangent have inverses called arcsine, arccosine, and arctangent. These inverse functions allow us to solve equations involving trigonometric expressions. For example, if y equals sin x, then x equals arcsin y. It's important to use the correct notation, as sin y can be confusing. It's better to write arcsin y. One of the classic problems in calculus is finding the tangent to a curve at a point. Imagine drawing a curve and wanting to know the direction it's heading at a specific spot. By considering secant lines through 2 points on the curve, and letting the points get closer together, we approach the tangent. This leads us to the concept of a limit, which is fundamental to calculus. Calculus helps us understand instantaneous velocity, the speed at a specific moment. While average velocity is distance over time, instantaneous velocity is the limit as the time interval shrinks to 0. This idea is captured by the derivative, which measures how a function changes at an instant. The speedometer in your car shows instantaneous velocity, a concept made precise by calculus. Derivative measures the rate at which a function changes. If y equals fx, then the average rate of change over an interval is fx plus delta x fx/delta x. The derivative is the limit of this average as delta x approaches zero. This concept is central to calculus, allowing us to analyze motion, growth, and many other phenomena. Acceleration is the rate at which velocity changes, and it's another example of a derivative. In chemistry, reaction rates describe how quickly substances are consumed or produced. Both concepts use derivatives to quantify change over time. For example, if A is the amount of substance A at time t, then dA/dt is its rate of change. Limits are at the heart of calculus. The limit of f(x) as x approaches A is the value that f(x) gets closer to as x gets closer to. Sometimes, substituting the value directly works, but in other cases we need to analyze the behavior as x approaches the target value. Limits help us define derivatives and understand continuity. Formal definition of a limit uses two quantities, epsilon and delta. For every epsilon 0 there exists a delta 0 such that if x a delta then fx L epsilon. This precise language ensures that we can rigorously prove when a limit exists. It's a cornerstone of mathematical analysis and underpins much of calculus. Limits have several important properties. The limit of a sum is the sum of the limits, the limit of a product is the product of the limits, and the limit of a quotient is the quotient of the limits, as long as the denominator doesn't approach zero. These properties make it easier to compute limits without always referring back to the formal definition. Not all limits exist. For example, the sine function jumps from -1 to 1 at 0, so its limit at 0 does not exist. Similarly, functions that oscillate wildly or grow without bound as x approaches a value may not have limits. Understanding when and why limits fail is as important as knowing when they exist. Sometimes, we're interested in the limit as x approaches a value from one side only, either from the left or the right. These are called one-sided limits. We can also consider limits as x approaches infinity, which helps us analyze end behavior of functions. These concepts expand our understanding of how functions behave. Sandwich theorem, also known as the squeeze theorem, helps us find limits of functions that are difficult to analyze directly. If a function is squeezed between two others that have the same limit at a point, then it must share that limit. This is especially useful for functions that oscillate or are defined in complicated ways. Function is continuous at a point if its limit at that point equals its value there. Polynomials and rational functions, where the denominator isn't zero, are continuous on their domains. Discontinuous functions can have jumps, holes, or other irregularities. Continuity is essential for defining derivatives and integrals. In dealing with compositions of functions, we often use substitution to compute limits. If gx approaches L as x approaches A and f is continuous at L, then the limit of f, gx, as x approaches A is fL. This principle allows us to handle more complex expressions by breaking them into simpler parts. Derivative of a function at a point measures how the function changes as its input changes. Formally, it's the limit of the difference quotient. fa equals lim x right arrow a fx fa/x a. If this limit exists, the function is said to be differentiable. The derivative is a new function that tells us the rate of change at every point. Leibniz introduced the notation dx for derivatives, thinking of them as ratios of infinitesimal changes. While modern mathematics doesn't use actual infinitesimals, this notation remains powerful and intuitive. It helps us remember that the derivative represents the rate of change of y with respect to x. Let's compute some basic derivatives. For fx equals x2, the derivative is fx equals 2x. For fx equals x, the derivative is 1. For a constant function, the derivative is 0. The power rule tells us that the derivative of xn is nxn for positive integers, and these basic results are the foundation for more complex differentiation. If a function is differentiable at a point, it must also be continuous there. However, the reverse is not always true. A function can be continuous but not differentiable, such as at a sharp corner or cusp. This distinction is important when analyzing graphs and understanding the behavior of functions. Some functions are not differentiable at certain points. For example, fx equals x is not differentiable at x equals because the graph has a sharp corner there. Similarly, fx equals has a vertical tangent at x equals 0, making the derivative undefined. There are even functions like Brownian motion paths that are nowhere differentiable. To make differentiation easier, we use rules: the sum rule, product rule, and quotient rule. The sum rule says the derivative of a sum is the sum of the derivatives. The product rule handles products of functions, and the quotient rule deals with ratios. These rules allow us to find derivatives of complex expressions efficiently. Power rule for derivatives extends to negative and fractional exponents. For fx equals xn, the derivative is nxn, even when n is negative or a fraction. This is proven using the quotient rule and for rational exponents implicit differentiation. Mastering the power rule is essential for tackling a wide range of functions. Derivative of a function is itself a function, and we can differentiate it again to get the second derivative, and so on. Higher derivatives are useful for analyzing acceleration, curvature, and more. For example, if fx equals x2 2x plus 3, then fx equals 2 and all higher derivatives are 0. The derivatives of sine, cosine, and tangent are fundamental results in calculus. The derivative of sin is cos x, the derivative of cos is sin x, and the derivative of tan is 1 cos 2x. These results are proven using trigonometric identities and the limit definitions of derivatives. Chain rule allows us to differentiate compositions of functions. If y equals f gx, then the derivative is f gx gx. In Leibniz notation, dz/dx equals dz/di asterisk di/dx. The chain rule is essential for handling nested functions and appears frequently in calculus problems. Let's see the chain rule in action. For example, to differentiate f(x) sin 2x, we treat 2x as the inner function and sin as the outer function. The derivative is cos 2x, 2 equals 2 cos 2x. The chain rule simplifies the process of differentiating complex nested functions. The power rule is actually a special case of the chain rule. For y equals f xn, the derivative is n f xn f x. This connection shows how the chain rule underlies many differentiation techniques and highlights the unity of calculus concepts. Imagine a balloon being inflated. The radius r changes over time t, and the volume v depends on r. Using the chain rule, we can relate the rate of change of volume to the rate of change of radius. dv/dt equals dv doctor asterisk doctor/dt. This practical example shows how calculus connects different rates of change in real-world situations. Sometimes, functions are defined implicitly by equations involving both x and y to find di/dx. We differentiate both sides of the equation with respect to treating y as a function of x. This method, called implicit differentiation, is powerful for handling equations where solving for y explicitly is difficult or impossible. Let's apply implicit differentiation to an example. Suppose x2 plus y2 equals 1. Differentiating both sides with respect to gives 2x plus 2y di/dx equals 0. Solving for di/dx, we get di/dx equals xy. This technique is essential for analyzing curves like circles and ellipses, which aren't functions in the usual sense. Calculus provides us with tools to analyze change, motion, and growth. By understanding numbers, functions, limits, and derivatives, we can tackle a wide range of problems in mathematics, science, and engineering. The concepts we've covered, domains, continuity, differentiation rules, and the chain rule, form the backbone of first semester calculus. In future lessons, we'll see how these foundational ideas lead to powerful applications. Calculus helps us optimize functions, understand exponential growth, and solve real-world problems involving rates of change. Mastering these basics will prepare you for deeper explorations in mathematics and beyond. To truly understand calculus, practice is essential. Work through exercises involving limits, derivatives, and implicit differentiation. Try sketching graphs, finding domains and ranges, and applying the rules you've learned. The more you practice, the more intuitive these concepts will become. Be careful with domains, especially when dealing with square roots and denominators. Always check for points where functions are undefined. When using the chain rule or implicit differentiation, keep track of which variables depend on which. And remember, understanding the concepts is more important than memorizing formulas. Congratulations on completing this introduction to first semester calculus. You've learned about numbers, functions, limits, and derivatives, the core ideas that will support your future studies. Keep exploring, practicing, and asking questions. Calculus is a powerful tool, and your journey is just beginning.